Welcome back. So we are now going to dive into this restaurant menu and look at all these operators one by one. So we'll start with an easy one. We'll start with the so-called set queries, which involve two relational tables. First, I need to tell you about the notion of a set and its closure. So if we have a set A, and we take an element X, and we apply some unary operator, tilde in that case, then we have tilde X, we can ask the question, is this tilde X going to be in A as well, or is it going to be outside? This is an example of outside, right? So we need the concept of saying that A has closure or is closed under tilde. What that basically means is that whenever you apply tilde to an element in A, you stay in A, right? It never leaves the set. So we say that it has closure, right? The same applies to binary operation. For example, if you take X and Y and compute X plus Y, we can say that A has closure under plus. An example is the set of integers that is closed under addition. If you take an integer and add it with another integer, then what you get is an integer, right? 2 plus 2 is 4. 4 is also an integer. The set of natural integers is not closed under subtraction, right? Because 4 minus 3 is 1, but 3 minus 4 doesn't exist as a natural integer, positive integer. So that would be a counterexample of closure. Okay. The reason I said that is that in the case of relational tables, we are going to try to use set operators. What can you do with sets if I give you two sets? What would be the equivalent of addition, multiplication? So of course, you cannot add or multiply sets, right? But what can you do with sets? I give you two sets. What can you do with them? Maybe on Zoom. Maybe people have ideas on Zoom.
Intersection.
Intersection, yes, absolutely. I see.
Merge.
Union. You could let me. So, is there another name maybe for merge? A different name.
Somebody says union.
Union, exactly. Yeah, it would be called union. So you can do the intersection, the union. What else?
Symmetric difference.
Symmetric difference. That's interesting. So I'm trying to think if you mean the subtraction, because you can subtract a set from another, but it's not symmetric. So maybe this is something I don't know. We should look that up, symmetric difference. What does it mean, symmetric difference of two sets?
So Wikipedia says it's the disjunctive union. So I think it's essentially.
Ah, yes, the disjunctive. So it's basically the union minus the intersection. Ah, very good. Okay, so that's that's the symmetric difference. Okay, well, I didn't know that. So yes, that's one other thing you can do with two sets. Thank you very much for this. Something else you can do? What would be the equivalent of multiplication for two sets? How can you multiply two sets? We've seen that before. It's the same as the multiplication sign, actually. Yes, cross product, Cartesian product, exactly. Yeah. So we are not going to do the Cartesian product just now, but what we are going to do is union, intersection, and subtraction, or maybe let's call it asymmetric difference. Okay, so let's take two relational tables then. This is a relational table on the left. This is a relational table on the right. And the question I'm asking is, can we compute the union of these two relational tables? So first I have to ask myself, why does it make any sense to talk about the union of two relational tables? What is the union of two tables, right? We only know the union of sets. So what is the union of two tables? Well, we saw that relational tables are sets, right? A relational table is a set of maps. So if you take two relational tables, you basically have two sets of maps. Right? These are two sets of maps. I have a set of 6 maps on the left, and I have a set of 4 maps on the right. So you can actually even split the maps, right? Make them explicit. It's just a different representation of the same, right? Where I actually put the attributes within the records in order to make the map explicit, right? So this is a map that is mapping A to K1 and B to 1, for example. This is another map that's mapping A to K5 and B to 5. This is a map that maps C to 3, D to K8, and E to 2017, right? So these are sets of maps. So I have 2 sets. Then I can take the unions of 2 sets, right? Of course I can. That's always possible. All right, so I'm taking the union of these 2 sets. That's also a set of maps, right? What's wrong with that? It's a set of maps, but is it a relational table? In the sense that we've defined it. Anybody? On Zoom, maybe? Usually people are less shy on Zoom because you can just type on your keyboard and... Is this a relational table? Anybody on Zoom? It's not. Why is that not a relational table?
The integrity constraints are not fulfilled or the attributes don't match.
Exactly. So we have a constraint that is not fulfilled. We do not have relational integrity. We do have a set of maps, but the supports of the maps are different. We have supports that have A and B, and we have supports that are C, D, and E, right? So technically, this is not fulfilling relational integrity, right? So the supports are not the same. So if we want to do the union of 2 relational tables, we have to put a few constraints. So what we've just established here is that the set of relational tables does not have closure on their union. You take 2 random relational tables, it's not going to be a relational table. So let's add a constraint. Let's enforce or ask that the attributes are the same. So now I'm taking 2 relational tables, and now the 2 relational tables have the same attributes, the same supports. Okay, but then I must add maybe another constraint, because at the end, if I want domain integrity, I also want a domain with each attribute of my outputs table. So it's best if that matches as well, right? Because otherwise I will have a problem if I try to union attribute A with strings and the other one with integers. Well, you could take a hammer and hit it, right? You could come up with a new domain that is the union of strings and integers, right? But it's not really nice. So let's assume the domains must be the same. So A is string, C is Boolean, and B is integer. Oh, no, that's on the, because I add on the slide after that. So now C is a Boolean on both sides. And third, but this is a virtual constraint. It's not a real constraint. The order of attributes should be the same. So now you must be thinking, what is this crazy guy telling us? We saw that the order of attributes doesn't matter in a relational table. And yes, it doesn't matter. So why am I telling you the order of attributes should be the same? It's more of a practical thing that when you actually use a real relational database system like PostgreSQL, the way they handle the order of the columns does not strictly always correspond to the theoretical relational model. So let me tell you that the reason I'm saying that is going to be just for the purpose of drawing the tables on my screen, right? When I draw the tables on my screen, if it's in the same order, it's going to be easier to draw the union without confusing you. But again, this is just paperwork because we saw in maps, the order of attributes doesn't matter. So this is kind of a fake constraint. Okay. But anyway, let's now take 2 relational tables that fulfill my constraints, meaning that they have the same attributes, check. They have the same domains, check. And I put them in the same order, but this is just for the visual on the screen. Okay, so can anybody tell me what the union of these 2 relational tables looks like? So you need to tell me, for example, what are the attributes of the results of the union, what are the domains, and how many records are there in the results? Yes?
So it would have the attributes A, B, and C with string, integer, and Boolean. And then I think there would be 7.
Yes. I'm playing the animation as you speak. Yes, 7 of them. Yeah. That's correct. That's exactly it. Thank you very much. So indeed, we have the union of the relational table R and S. We gave it a new name. We call it T. But indeed, it has exactly the same attributes N, B, and C. It has the domain string, integer, and Boolean, and it has 7 tuples in there. Why is it that these are 7 tuples? Could you imagine a case where I might not have the sum? So here 7 is 4 plus 3, right? Could you imagine a case where I might have only 6 tuples? Yes? Exactly, if they are duplicates. So if they are duplicates, like we have the same record in both R and S, then indeed, when you do the union, the duplicate will disappear. And I think we have a student on Zoom who agrees.
Indeed, after identical entries.
Yeah, awesome. And I think I have an example. Well, I should have put it in a white font because this is impossible to see. But basically, I'm saying if you have twice the same thing, then you eliminate duplicates. So I think my intent, it's actually better that you don't see it because I think there was even a typo here that it's supposed to be the same here and here. So pretend that this is exactly the same here and here, but in that case, when you do the union, then you just have it once, right? So this is an example or counterexample that the total number of records in the results can be at most the sum of the numbers of the original tables, but it can also be less. It doesn't have to be equal because we eliminate duplicates. Why? Because we have sets of maps, sets. This is the reason why we do not have duplicate records. Okay, who can tell me what the intersection of these two relational tables is? We check the constraints, right? A, B, C, they have the same attributes, the same domains, and so on. So can anybody tell me what the intersection looks like? We have the empty set. Somebody says the empty set. Any other answers? Yes, exactly. So actually, I got the trick. It's one of you, I think. Was it in this lecture in big data? But you gave me a trick in order to make this thing disappear. I need to open the chat and I need to close the chat. So let me open the chat and close the chat. Yes, you got it. Okay. So can you confirm your answer? Yeah. Yes, exactly. So these are the records that are on both tables, 2 records. And we even have also on Zoom other students agreeing. Okay, awesome. So this is the intersection of these 2 relational tables. By the way, I didn't mention it, but I use scary mathematical notation here, right? So this is a union sign. It means R union S, right? This is what I meant with this binary. It's like plus or multiplication. So this is your union. And this is the intersection, this sign right there. Right. Okay. Why do we not need duplicate elimination? Well, it's kind of by construction, right? In the way we were basically looking for the records that are in both. So when you do that, you actually come up with unique records. So that's why. Yeah, not that it's very interesting to say, but yeah, I said it. Okay, so there are no duplicates left. And finally, subtraction. So that would be, I think, what could call the asymmetric difference, by opposition to the symmetric difference that one of your colleagues was suggesting. So the subtraction of R minus S. Can anybody tell me what R minus S is going to be? There is a bit of help here. Okay, the easy part. Yes, go ahead. What are the attributes and domains, and then the contents? Yeah. The microphone is so people on Zoom can hear you too. Yeah.
String, integer, Boolean, and then the 2 rows that are in light blue. So bar 2 false and foo bar 4.
Exactly. Yeah. Thank you very much. This is correct indeed. So this is the subtraction. This is all the records that are in R, but that are not in S. So this is why the first and third disappear, because they are in S, and this is what we get. Note that that's the reason I was confused when one of your colleagues said symmetric difference, because this one is asymmetric. S minus R is going to be difference. Union and intersection is, what is the name again? You can swap them, it's commutative. So this is commutative, union intersection, but this here is not commutative. R minus S is not the same as S minus R. By the way, I use the minus sign here. I think there is another notation that is not a horizontal line, but slightly diagonal, like a descending minus that I think is maybe more common, like a backslash. Okay. And yeah, we don't really need to worry about duplicates by construction. So by the way we constructed that, looking for table R and removing tuples that are in S, then we don't have to worry about having any duplicates in this construction scheme. Okay, this here is a counterexample. I wanted to make the point that it's not commutative. The cool thing is that when you want to prove that something is commutative, it's complex because you need to prove it for all possible items. But what's super cool about proving that something is not commutative is that all you need to do is pull a counterexample out of your bag. And this is the counterexample I'm pulling out of my bag, right? So this is R minus S and S minus R, and you can just notice that this is not the same, and that's enough to show that it's not commutative. Okay, so far so good. Who is following? Okay, people on Zoom, are you following too? Raise your hands. Oh, wonderful. Plenty of people. Yeah. So I know that you're in front of your screen, right? Because you never know. People can also switch on and then go somewhere else. But it's nice to see you here. All right. So filtering queries now. So this is no longer about sets. So I'm going to take one relational table and I'm going to do things or manipulate it to filter things, as the name indicates, filtering queries. I have good news. I don't actually have any constraints on the input. I can pretty much take any relational table as long as it fulfills my three constraints: domain integrity, relational integrity, and what's the third one? Atomic integrity. Yeah. Okay. So here's a relational table, and I'm going to do what is called a projection. It's a projection on a list of attributes, so you need to say which list of attributes you have. So let's say A and C. Can anybody guess what the result of that is going to be? Intuitively. On Zoom, maybe? I know there's at least 15 people on Zoom because you raised your hands. Any guess? So maybe start with the easy part. What attributes? Yes?
Only the A and C columns.
A and C, yes. What domains?
Without the B columns, which is right.
Exactly, B disappears, yes. What domains do we have in that output table? Mm-hmm. Yes, exactly. So string and Boolean, right? So exactly, the domains do not change. Yeah. And what about the records? How many records in the projection? 4 records. And what do they contain, these records? The same information as A and C. So in that case, indeed, so new name, specified subset of attributes, A and C, the attached domain, the same ones, and the projection of the records on the attribute subset. This is a mathematical thing. When you have a map, mathematicians call it a partial function. When you have a partial function, you can restrict the domain of definition of a function by just removing some of the mappings. In fact, mathematically, this is what happens. You basically restrict each map, which was originally defined on the domain of definition was ABC, and you just restrict it to just A and C. So it's a mathematical thing you do on the maps. But visually, it's much easier than the whole math because all you need to do is just remove the column B, right? So you get these 4. Actually, if you use spreadsheets, it's easy. I mean, in Excel, you just select the column and do Control-0, at least on Mac, and then the column disappears. And there you go, you have a projection, right? So that's something super easy to do in a spreadsheet software. Will it always be the same number of records? Or can you imagine a counterexample when it's not the same number of records in the outputs? Yes? Maybe yeah.
In case like foo1 was false as well, then when you take A and C, it's going to remove the duplicate entry because foo false will be twice.
Yeah, exactly. So the idea is that it can be at most the same number of records, but you might obtain duplicates that were not duplicates before, but they become duplicate if you remove a column. Because as you said, imagine you have foo1 false instead of foo1 true. Then foo1 false is not a duplicate with foo3 false, right? They are different in the original table. But if you remove the number in the middle, 1 and 3, that was the only thing that was making them different. Now you have the same thing, foo and false. So in that case, the output will have less records. Okay, visually, this is what it is. You really just pick some columns and delete the others, or hides them in a spreadsheet. Okay, and this here, I was lucky. I had exactly the slide to support the illustration of what you said. So this is the case where now we have foo1 true and foo3 true, in which case we need, this would be incorrect. On the right, you wouldn't have a set because there's the duplicate. This is now a set of maps. You just eliminate after the projection, right? Okay, now about the scary thing in the middle, right here. This is how you denote the projection. So it's pi, that's the Greek letter pi of A and C. So these are the attributes you want to project. And this is a function that takes a relational table and returns a relational table, right? Now you can say, if you want to sound fancy in a party with your friends, you're going to say that the set of relational table has closure under projection, right? Because the relational table projected is also a relational table. Okay, so this is pi, A, and C. And we'll see there's plenty of other Greek letters that we will see. We'll see sigma, gamma, delta, and so on. And they will be all over the place. This here is the relational algebra. Okay. Okay, that was projection. Projection worked on the columns, right? Can we do the same thing on rows? And the answer is yes, we can. Yes, we can. And what we need is a predicate. It's some yes-no question that we can ask for every one of the records. As an example, we could have as the yes-no question, is the value of B smaller than or equal to 2? That's my yes-no question. The fancy word for that is a predicate. So we use the predicate B smaller or equal to 2, and we ask the question for every record. Can anybody tell me what the output relational table will look like? As always, you need to tell me what attribute, what domains, how many records, and what they contain. Yes?
Attributes A, B, C.
Yes.
Domain, string, integer, boolean, and then the first 2 rows.
Yeah, the same domains. And you said the first 2 rows. Yes. So you see that if you evaluate that predicate B is smaller or equal to 2, it's going to be true for foo1 true. It's going to be true for bar 2 false. It's going to be false for foo3 false because 3 is greater than 2. And it's going to be false for foo bar 4 true. So you eliminate that as well. I think I even have, yes, let me show you this animation. So I put in this dark green here, the first 2, and indeed, these are the ones you keep. Now, we were lucky that they are all together and these were the first rows, right? It's not always the case. It can also be a random distribution of rows that you take here and there. Okay. Now, we have a new Greek letter that we can add to our collection, which is the letter sigma. Right here. You see pi is P, right? So that's projection, P as in projection. Sigma is for S as in selection. So this is why we use sigma. Now, for the projection, we had a list of attributes. For the selection, what do I have? I have a fancy mathematical formula that is a yes-no question. So in that case, it's b smaller or equal to 2. Now, I can actually have rules of how I build my predicates. And again, here it's a restaurant menu. What can you use for your predicates? Well, you can use comparisons. You can use, here again, I should have put it in a white font, but anyway, a lighter, because you can barely read it. It can be lower than, greater than, lower or equal, greater or equal, equal, different. So these are all the comparisons. You can also use maybe and then or, right? So let me tell you, because who never saw these symbols there on the top left? Some of you, right? Who knows what these symbols are? Can you tell us? Maybe with the microphone. So I'm asking about these ones right here. What is this thing here?
These are and or not.
Exactly. This is called a conjunction. This is an and. This is called a disjunction. This is an or, and this is called a not to negate. Intuitively, it's really what you have in your everyday life. You can make sentences with or, it's raining and I have an umbrella, or it's raining or I have an umbrella, and so on. And you can also say it's not true that it is raining, and so on. So you can basically combine. So then you can say things like b is greater or equal to 2 and d is smaller than 3, or d is equal to 3, and so on. So you can do all kinds of combinations. Then you can also use, and again, here I should have picked a lighter font. You can have all the arithmetics, addition, multiplication. That works if you have number domains, right? If you have numbers on your columns, you can add them, multiply them, divide them, modulo, so plenty. You even have logarithms, trigonometrics, and so on. You have so many things you can do, right? And finally, you can add parentheses. You need parentheses whenever you have an issue with the order in which you do things. Like, you know, right? If I tell you 2 plus 3 times 4, the result is actually 14. It's not 24. It's not 20, right? Because if you have multiplication, you start by the multiplication and then do the addition. But if you're not happy with that order, you just add parentheses in order to force a different order. You could say 2 plus 3 in parentheses times 4, and then you get 20. Okay, so anyway, this is what computer scientists call context-free grammars. This is actually a way you can build a whole language that you can then parse with a piece of software. And when you have defined a language like that, this gives us a language to build predicates. And once we have a language that we are allowed to use all of these symbols, then we can build all kinds of much bigger and more complex predicates in there. So we can do whatever we want, all right? And then we can apply the predicate and get the output table. We don't need to worry about duplicates here. Because all we do is answer the yes/no question, and we keep the rows for which the answer was yes. So there's no risk that a duplicate would actually emerge out of nowhere, right? So we don't need to worry too much about that. So selection is like that. In fact, you can also very easily do a selection in your favorite spreadsheet software. The way you do that is that you select the entire region where you want to do a selection. Then you need to do somewhere in a menu like data, auto filter or something like that, auto filter. And then it adds these fancy rows in the headers on the top row. Then you can click on one of these and then select or deselect values. And the spreadsheet is automatically going to select by removing and adding the records. I'm pretty sure a lot of you already did that. Who already did that? Nobody? Nobody ever used a spreadsheet in that way. When you have a list, for example, we do it actually. You know, I did it just the other day when I sent an email to mobility students about the distance exam. I actually exported to an Excel file the database of students. Then I did this auto filter, and then I selected the program column. I only kept selecting the mobilitet, mathematics, mobilitet physics, and so on, and deselected everybody else. And then I copied over the list of emails for this. This was actually a selection that I did, right? But I did it in a spreadsheet. Okay, for whom is that clear? Okay, very good. Okay, but of course, when I'm talking about spreadsheets, it's just to give you an example, because in reality, when you deal with complex data sets, you should not be using a spreadsheet software. Because imagine you're a big company and you use a spreadsheet and you make mistakes, it's going to be in the news front page that you made that mistake. And that actually happened, I think, in the UK 2 years ago. So if you don't want to be in the news, use a relational database and not spreadsheets software to make sure that it works. Okay. Let's move over to also something fancy. It's called an extended projection. So far, when I showed you the projection, all I did was specify a list of attributes and we keep these attributes, but we could not modify or compute things. What if we want to compute things? Well, if we want to compute things, we can actually extend this pi notation by not just listing attributes A and C and D, but I can also specify that in D, because D doesn't exist here, I'm creating column D. But then I need to specify how. And here I can say that column D is defined as B plus 1. Right. This is this little row. So this little row, the reason we use it is that it's kind of the assignment operator. When you learn how to program, it's a popular notation. Okay, now this is more difficult. Who can tell me what the output relational table of that is going to be? Anybody? As always, right? The attributes, the domains. Okay, you want to try? Let's go.
AC with, and then one D.
Yes. Mm-hmm.
And then string Boolean for A and C, and D, I guess, would also be integer.
Yes.
And then for A and C, it would be all the same as those rows. And then D would be everything in B, but one greater. So 2, 3, 4, 5.
Yes. Perfect. That is correct indeed. So what happened in there, you inferred the domain of D. You didn't just copy it over as you did for A and C, but you inferred that D is an integer. How did you do that? Well, this is actually not trivial at all. It's basically by looking at that, you see, okay, if I have an integer and I add 1, it's going to be an integer, right? So this is an inferred domain in there. And then indeed, this is all correct. You see that B is computing, D is computing out of B. Do we have a question? No questions? All right. Checking the time. We still have a bit of time. Okay. So, okay, now I've already done 2 of my menus, you know, the set queries and the filter queries. I'm already in the third one, the renaming queries. So this is yet another Greek letter, which, do you recognize it? Row, exactly. This is a row, RHO if you write it in English. So this is this here, this little symbol here is a row. And here we say A, a row D. So A becomes D. So we rename attribute A to attribute D. So what is the result? That should be easier than the extended projection. Maybe somebody on Zoom can tell us. Okay, people of Zoom, anybody? Maybe they are cooking already because lunch is, okay, we have an answer here.
Row A is going to be called D.
Yes.
And the D, B, C attributes.
Yes.
Same table column name is now D, that's right.
Yeah, exactly, it's the same. We just change A to D, that's pretty much all that changes. And the fancy way of putting it is this row A becomes D of R. Okay, so you see this is really calculus, but instead of numbers, I have relational tables. Okay, I can also rename a relation, but here is going to be trivial mathematically because all you really do is S equal R, and now you have a table that's called S. Now I know how itchy it is for mathematicians because technically, when you do mathematics, and this is where computer scientists might do things differently, when you say X is 2, 2 doesn't know that it's called X, right? It's just 2 and X is equal to 2. When you have a function F, the function doesn't know that it's called F. It's you who are calling it F. So technically R shouldn't know that it's called R and S shouldn't know that it's called S. So normally it should be the same thing. It's just an assignment. But you know, in computer science, we also like to sometimes let the things that we manipulate, we let them know how they are named, right? So this is kind of what we are doing here. So it's like some I don't know how to call that, some sort of consciousness or self-consciousness of relational tables, that they are sentient beings, and so they know how they are called, right? So this is R and this is S. And what we do is simply that we replace the letter R with the letter S in order to create the output. Right. I'm almost ashamed of saying something so trivial, because really it's just saying, okay, R is not now known as S. Okay, for whom is that clear? Okay, very good. Okay, now, if you're a mathematician and you want to, point your finger and say, no, you cannot do it that way, you need to do it rigorously. Then what you do is that you pass the S as a parameter to a row function, but then that's renaming a table. And now it's mathematically consistent because the information that it's called S is actually in the parameter. Okay. Okay, that actually takes care of my third box. Do we have time for the binary queries? We'll maybe start, maybe not with all the joins, but at least still have a few minutes, the Cartesian product. I think I call them binary queries. I actually used to call them binary queries, but now I call them join queries. I think I changed it to join queries. The reason is that you could argue that the set queries are also binary queries, right? Union, intersection, subtraction, it also takes two tables. So this is why I wasn't quite happy calling them binary queries. So let's call them join queries. Okay, so this is the multiplication of two tables. Remember that relational tables are sets of maps, and we have two sets. One of your colleagues on Zoom suggested that we can take the Cartesian product of sets. And that means that we can take the Cartesian product of tables. So my question, can you tell me what the Cartesian product of these two tables is? Anybody? As always, the attributes, the domains. Nobody in the lecture hall? Okay, let me ask it that way. Can you raise your hand if you know, but I promise I will not ask you. Just for me to know. Who knows what it is? Okay, very good. And as I promised, I will not ask.
5 attributes.
On Zoom, yes?
5 attributes.
5 attributes, yes. What are they?
A, B, C, D, E.
Yes. How many records? 6. Why 6? How did you get 6? It's the correct answer, right? I don't want to scare you. This is correct. I'm just asking why it is correct. Yes, I saw a fancy formula there.
Cardinality of R times the cardinality of S.
Exactly. These vertical bars mean cardinality. So the cardinality of R times S, so it's 2 times 3 is 6. And the reason is, so what are now, can you describe what these records are? These 6 tuples, these 6 records? Give me one example of output records, just one.
One, true, 2, and 1.
Yes, exactly. So this one would be what you get if you take this record right here and this one right there, and you combine them to this. So basically, you need to do all possible combinations, right? So you see 3 with foo 1 true for each one of them, and 3 with bar 2 false, and you have again 3. For whom is that clear? All right, wonderful. So I'm going to stop here with plenty of raised hands, which is a delight. I'm just going to ask you the usual question to check that you followed, and next week we'll continue with the joins. So just a few seconds, please, before we go. This one. We're even 6 minutes ahead of time. So you even probably will avoid the queue in the mensa. Oh, this is wonderful. Okay. because that was theory, right? That was heavy theory. So I try to put it simply, but it's really nice that you're following. All right. So we'll continue next week. Thank you very much, everybody. And I'll see you next, enjoy the exercise session, and I'll see you next Friday at 10 again. Thank you very much. Goodbye.